All right, before we get started, there's a few things you have to understand. We can accelerate light. There's no question whatsoever that light is accelerating. And here's before it accelerates. It's just this. It's just starting to accelerate now. And then it accelerates full strength. Now, not only is it going forward, it's spinning. And that I can prove as well. This one we're looking this way, and it's spinning, and it's creating that pattern as it goes through the slit. So I can prove it's spinning, and I can prove that we can accelerate it, and I can prove the blue is much faster than the other particles. It's coming in here like this, spinning like this. The little white particle is the actual glowy part of the electron. And it's spinning the right-hand spin, which is correct, and it's starting to slow down. And you can see there's the dipole part of it. Blue's too fast to work with. But then you go down to the green, which is very fast too. And here's the particle as well. Now this is, you see it's polarized towards the Earth, even if it's going that direction. The black and white are, this is going that direction, this would be a downspin. And it's just about ready to flip, I think, because they flop and go back and forth depending on how much impact they're running into. And that's why they spin around in circles. Now the red is slow, and we can see the red quite easily. You see the photons of red? And the reason they're looking like photons right there, a photon, in my mind, it only really happens when it bounces off of something. These think they're bouncing off of something because of the reverse wave here. And this whole area here glows like crazy. You can see it right here. Well, here it is right here. This particle, and it is a particle, it has a wave around it, a field, just like two magnets. You put them close to each other, you can feel it. There's nothing there, but you can feel it. And that's what it does. It goes through and pushes everybody out of the way, and all of a sudden it started to accelerate. And here it felt like it hit a wall because of the reverse effect. That's why these are all lit up as well. Same as this. You never see any of them, unless this one was accelerating and these ones are being pushed backwards. Same thing. Acceleration and reverse concussion. And right here, this thing lights up like a photon because it thinks it just hit a wall. Photons seem to be bouncers. As they come, you don't see them in the other areas. There's no photons up here. You don't see them. They might be there somewhere. But the only reason you see these are because they're being pushed back at, and they're starting to show up as something. These turn into actual photons because they're right in the line of fire. They're going to end up exploding here. And they do divide. They do what is called fission, and they come back in fusion. Here is fission. The black and the white break apart. There's no other way to explain it. That's fission. And back here, the white comes through showers and joins back to the black over here, and that's fusion. So it's fission and fusion of the most tiny particles, which is photons. And they're starting to understand this now, I hope, because that could lead to free energy. Because all you got to do is rip the white away from the black, and it's sitting here waiting to get back to that black, and it really wants to get back. And that's what electricity is. It just goes through a wire or whatever to get back to that black. And we're ripping them apart. And I don't see any reason we couldn't collect them here somehow and keep them apart from the black. And so you want to get back to the black, you got to go drive this car, or you got to light that light or whatever. And it'll do it. It wants to get back to the black. And these are the same particles they found at Fermilab. Exact same, identical particles. These are our black ones. And they have a glow around it, see? The black ones have the glow. And the white ones can get big and small, and they're just energetic. They just have nothing, no mass to them. When you see an atomic bomb go off, and the first thing is the white pulse, the houses just burn up, and the smoke doesn't even blow away. It just burns up like this, and then bam, the black ones come behind and knock it down. This should be understood. This should be looked into a lot quicker than it's being looked into. Because this makes, this cosmic microwave background dipole, I don't know what they're talking about there. That's to justify the Big Bang. They grab a hold of a theory that doesn't work, and they just can't let loose. Anyway, I didn't realize it until the end, basically. She's basing everything on the speed of light, as are these scientists saying we're going 3 times faster than we should. The speed of light is not consistent. It's nowhere near consistent. The speed of light is so variable, it's unbelievable. And it's because things that it passes through slow it down. All the things that the nonsense is based on the speed of light being consistent, and it's not. Space is not a vacuum, and anything that gets in the way of light will slow it down until it becomes the cosmic microwave background. What does that mean? It means they're particles that aren't moving anymore because they slowed down. And she based everything apparently on that. I would love to discuss this with her. But until we get away from this nonsense that slight light never slows down, we're lost. And that's what I believe this is being based on. All right, so she's saying if the standard cosmological model is wrong, this could resolve the discrepancy. Well, yes.
The discrepancy simply because the motion of the radio galaxies doesn't have to agree with that of the cosmic microwave background. They basically decouple at the distances that this study looked at, so the problem disappears. This result is compatible with a study I told you about several years ago from the group of Zubir Zakar and collaborators. They did something similar with quasars, and they also found that we move too fast relative to the quasars. I give this paper a 1 out of 10 on the bullshit meter. I didn't find anything wrong with it, but I don't trust statistical significance estimates and astrophysics in general. This result from the Zakar group has been mostly ignored, and I'm afraid that the same thing will happen to this new result. The issue today is still the same as it was then. It's not that astrophysicists dismiss the findings, it's that they can't agree on what a better theory for our universe should look like.
And they won't engage. And as you, a physicist, Savine, I would love to engage with you and discuss my theory of dipole electron flood theory backed by my evidence, not by some bullshit. I agree with you. It's just nonsense that they're spreading now.
It's kind of like the Australians voted in 1999 to keep the Queen of England the head of their state. Not because they liked the Queen so much, but because they couldn't agree on who else should do the job. And that's why I'm pretty sure that, at least for now, the standard model of cosmology will remain on the throne. Bet you...
All right, here it comes. All right, this redshift thing is just crazy. It would make us the center of the universe. Because they say when the Big Bang happened, everything is getting pulled away. Well, it's getting pulled away this way and that way and this way and this way. So we would have to be the center of the universe. Because it's redshifted every direction they look. All it is slowing down as it goes through all the particles that are in front of it. Because no matter where you are on the Earth, it's the same kind of redshift. It can't be pulling away this way, and it doesn't affect this. I say, well, why would it be pulling away this? It can't be. It's like sucking the earth. It's crazy. And I went through this with Chad and said, well, it was just insane. I just don't understand it. Now, all it is the light gets slower and slower down into these radio waves from fast. Light can come really fast, and that's in a really powerful X-rays and so forth. We can only see in this very, very limited area. And then it gets smaller and smaller, infrareds, microwave do the, the cooking, and the infrared is like just warming you, and it's the intensity of the light that's hitting you, how fast it's spinning, basically. The spin gives its power. So what they're doing, talking about, they can see here because of the redshift, we can see the furthest thing in space. No, we see the thing that had to go through more other stuff in front of it than everybody else. That's all. The dipole electron flood covers everything. It's the only theory that works, and it works for everything, 100%. Okay, as you're going to see, the white electron and dark muon are basically the single unit called a dipole electron. All right, they have to have the dark matter, and that is dark matter, and it's solid, and we can walk on that. You can't walk on light. Well, maybe you can, but if you can, you're probably going to be Jesus. All right, my claim is there's only two particles that exist. There's a black one, it's a muon, and it's hard and solid. It's just one chunk. The white one can get big, can get small, but they have to be together. Their nature is to be attached to each other. That's the strong nuclear force. And there's 1,839 of these or so in a proton. Now, a block of them like this, back to back, which is, again, their nature to attach here and attach here, attach here, attach here. Everybody's happy. That's a photon. Depending upon how fast that photon, let's say that's it right there, how fast that's spinning forward determines its color. And if it's going fast enough for our eyes to see, or is it just warmth or whatever. And this is static electricity, that's static. And then real electricity is just a white. And you have to have the white in one place and then attract it to the black. That's electric flow. So this covers it, it's done. And it's all over space, it's everywhere, because these are being spit out of every luminous source. All right, I've been working with some guys that are pretty talented. Now, this is Mason. He has a paper, it's called the Zeeman effect, up on academia.edu. And this is what space looks like. These are the fields that are in space. There's darker areas where there's not so much pushback, and then there's whiter areas. But it's a whole mix. And these ones here, these really intrigue me, the orange ones. I'd like to know about this a little more from Mason. We've been trying, we have a hard time hooking up together here. He's busy, I'm busy, but I'm looking at this, and it's very intriguing. It's very intriguing. It almost looks like, there's so much to look at, but here's the way he does this, is my interpretation. I'm not an expert by any means, but I believe he's doing what is called stacked and layering, where you take multiple images at different frequencies with different filters. So what does that mean? Well, let's just see if we can figure it out. I'm going to be 100% honest with you. I don't know what he's doing. All All right, Mason is doing some phenomenal stuff. I'm not exactly sure how he's doing it or what it means, if it means anything, but I think it does. Because I'm seeing dipoles no matter where we look. No matter what he's sending me, it's dipoles. And I saw this with Dylan Carpenter long ago. And of course Rod Warren has been doing this forever. This is Rod's work. And this is nothing but dipole electrons. Now, when you convert them into their actual color ranges, you can see the black is just totally black. That's it. And the black one here is totally black. The white ones can get smaller and they can get bigger. And it's because they're hitting the white particles in front and the particles going this way. This will charge up and then flip, and that one will come in front. This is downspin right now. When this one comes in front, it'll be upspin. And they always are in alignment with Earth, magnetic north. And I've seen these, the green, the red, the blue, they're all the same. Only they spin faster. The blue is like a rocket ship. And the green is somewhere in here, and the red shifts out to here. And they say it's because the whole universe is pulling away, so it's making the light turn red. No. The light's turning red because it's bang, 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 bang. It's knocking into something and just slowing it down. It's like hitting a bale of hay and then another one and another one and another one. And the car just eventually becomes the cosmic microwave background. And of course, you've seen this a million times. This light is accelerated. It's accelerating. There's no other way to understand it. It's just unbelievable acceleration. And this extreme luminosity means that the white is left the black. That's fission. And this is literally nuclear fission. They come back together here and that's fusion. And this is exactly what they do with the heavy water. And they create this glow in the water because they're creating all of these electrons. And we're doing it by crushing the fields together through a Venturi. And there's the particles, and there they were from Fermilab. And this was a long time ago. I tried to work with them, and it didn't work out well. So anyway, I'm going to show you what I have to say, and maybe Sabine will look into this. This is not silly. And Mason's new work is phenomenal. Absolutely phenomenal. When you say this is the universe we live in. These are all fields. And they're, again, stacked and layered, and I don't know that much about it, so I don't want to talk too much about that. But I do know that I'm seeing dipoles literally everywhere. And then even masses, an entangled mass of dipoles next to each other. Same thing here. A lot of glow here and a lot of dark here. It appears that is the entanglement of mass is to turn into dipoles. It's not something dipole happened because of a big bang from nothing. Isn't it nothing into everything? And it's pulling away from everything at one time. We have to be the center of the universe. It makes no sense. None. Zero. All right, here's the trouble with the internet and Google and chat and all of them. They just repeat what the academics say. It's not mainstream, so dipole electron flood theory is not accepted by physics community and is considered a fringe or speculative theory. Now listen to this. Lack of evidence. I'm the only one that has evidence. There is no experimental evidence. That's total nonsense. I show you the experimental evidence. No experimental evidence to support the central claims of the theory. I support every claim I'm making, such as the nature of protons and neutrons or the existence of dark muons. I show the dark muon, neutrinos, and white electron neutrinos as described. I show them physically, actually, experimentally show them. Conflict with established physics, yes. The theory contradicts well-established physics in modern physics, such as the standard model of particle physics and quantum mechanics, which cannot explain dark matter. They can't even explain how things drop and fall to the ground, gravity. Plus, everything else is wrong. They base all of their assumptions and guesses on the fact that there's a vacant vacuum universe. There is not. It's totally saturated with the particles of light, dust, and all kinds of things. And light slows down. Light has mass. Let's get through it. Let's go to it. All right, let's just start off with this. There is no vacuum in space. Empty space isn't empty. They know this. Nobody's disputing this. This was from 2013, Fermilab. Don Lincoln, I went around and around with him. I say there is no vacuum. There is no vacuum. He's saying the same thing. Only they say that light has no mass, so it just goes through. It doesn't matter if there's a vacuum or not. Well, that's just not true. Light has mass. Okay, this is from Fermilab, from an article I'll show you in a second. Don Lincoln says that there's a black particle that they have found, the smallest one they have found, but it always has a glowy edge around it. And then they have a glowy one that has no real mass, and that has mass. And that's exactly what he says in that article. And there's the black one, and there's the white one together. These two are together, they just never realized it. And this is photons, because we used light. They used big, huge things, smashed them together, and they went every which way, and they had chunks here and chunks there. We used light, so we didn't have to see all of what they call a particle zoo. We were able to see exactly what light is made of. Now, we all know when things explode and smash and so forth, there's usually some kind of brilliance in the ranges of just banging things together and causing energy that you don't have enough energy to shoot out photons. But once you hit a certain level, then you start to, above these here, you get into infrared and visible, and then you have to have enough vibration, enough frequency to emit an electron or a photon, or a dipole electron really is what you're emitting. So I say this is exactly what they were seeing at Fermilab. And then we were able to explode those and create fission and fusion. And then for chat and all these other AI devices to say, oh, he doesn't have any information, he doesn't have any experimental evidence, there's nothing to show it. There it is right there. And it's way ahead of what CERN and Fermilab was doing. And I went to University of Geneva, and I didn't go there physically. I took a course. And I told them about what we were doing. And this goes years and years and years ago. And they finally did agree, yes, CMOS was the way to see this. We did this with just a regular cell phone, smartphone. Galaxy S3 from 2012. And this is 2013. Don Lincoln was putting this up, and here's exactly what it was. Same particles. I copied this right off of his page. And it says that the black one has all the weight, and the white has no weight. And these are the smallest particles I can see. But this has a field around it that causes it to have energy. I agree with both of those statements. Only they don't realize those are dipole electrons when they're back to back. They call them Dirac neutrinos. I go along with that. That's fine. Call them anything you want. It's a black one and a white one. This goes over 10 years ago, 12 years ago. So that's a photon, and I say that has mass. And I can prove it in a number of ways, which I have. This blue laser, that's coming in very fast, and then it's slowing down. Light slows down, light speeds up. The medium that it's going through obviously has an effect on it, but in space, there's nothing but mediums. So it's going to slow down in space. There's just no getting around it. Now, any picture you see of space with the Hubble or Webb telescope doesn't matter. You're going to see stuff like this. I have a special guy that I'm working with now. He's doing something more advanced than they are, as far as I'm concerned. And this is what it looks like right in the neighborhood. This is just looking out in space. There's dark spots, there's glowy spots. Most of them are dipoles, but I can see that there's different types of dipole activity. There's exactly black and white together, and then there's cloudyish white and cloudyish black. But I don't care. If you're coming through that, you are going to slow down. There's absolutely no question about it. All right, so now space is not homogeneous, obviously, and it's not vacant, it's not void. This has been known. It's not an unknown thing. This is what bothers me. Now, if this is correct, and we are on a spinning galaxy like this, and I believe that's true, from these distant space shots, they can see these pictures. Now, these particles are coming through space, and they're spinning around, so we are on one of these arms of the galaxy of the Milky Way, let's say. And I believe pretty much most of them end up going around. Boy, that's a tough one. That one there I got to really look into, because they could be. I'm seeing all kind of different looks to them. But normally I think of a galaxy as sort of spinning and spiraling and coming into itself. Check this out. This guy's got some serious stuff going on. Now the only problem is he's got to get some kind of new filtration devices. He doesn't have enough money, so trying to save up to get some money to do this. Or if somebody wants to contribute to Mason so that he can do this. Because, this stuff, he's got some pretty serious equipment, and the things he's showing are just mind-blowing. That, I think, is, I'm not sure, Jupiter or Saturn. I'm not even sure, to be honest with you. He sends me all kinds of pictures, and he's got an article on academia, the Zeeman effect, I believe, and he shows a picture of the sun is a black and white ball, and he says that this is not CGI, it has nothing to do with that. It's an actual physical picture taken of the sun with some kind of filtration devices. He's got something going on very, very serious. And hold on a second. Here it is right here. CMOS, that's complementary metal oxide semiconductor silicates. Sensor data and the Zeeman effect. Now, this is what I was fighting with Fermilab and CERN about, is that you could use CMOS to see these particles, which I was showing you. I just showed you. Those are particles. Those are particles of light. The red, green, blue, we see them all. And here's what he found. And he claims this is no picture. This is a real, actual physical picture. He took Sunday, August 3rd. And this is the CMOS sensor data and the Zeeman effect, a novel approach to dynamic electromagnetic field imaging. There's an imaging of the fields. And this is Mason, and this is our sun. The image shown above is not CGI or an artist's rendition based on data. It is physically, as far as I know, I got to get back and work with him some more, but it's all about the Dipole Electron Flood Theory and CMOS. And he goes on, he's a very accomplished guy. Now, what we need to do, though, he should have some funding. And these are the kind of guys that get no funding. And the things I could tell you about, well, and I will probably tell you about them, but these are the kind of things that are concerning to me, that there's no normal people doing this stuff. You have to say what the other guy says, or they put you out in the field. That's what happens. And that's what happened to me. It's what happened to Velikovsky. It happened to everybody. And it will happen to him too, unless we can break through this wall of denial. Okay, back to Sabine. Here we go. I don't know what she said. I haven't watched this. Here we go.
Our solar system is going 3 times faster than it should. 1,000 kilometers per second faster than what the textbooks say. That's what a recent data analysis found. And it's a big deal because it's incompatible with how we think the universe works. How do we know how fast the solar system should go? And where are we going? Let's have a look. Physicists' best current theory for how the universe works has it that most of what's in the universe is weird stuff called dark matter and dark energy. These dark ingredients, which together make up 95% of all the matter and energy in the universe, are necessary to make the theory fit the data. That works, but it seems a little crazy, and in the past years this idea has begun to crumble at the edges. Maybe this new data will be the final nail in the coffin. The new data.
Okay, so she's talking about the final nail in the coffin, and there's been so many nails in the coffin, I can't believe it, and they still continue to keep saying a Webb telescope just found something further. The only reason is the light is slowing down quicker and quicker. The thing isn't further away because it's being stretched and pulled away because the universe is expanding. All this is based on the Big Bang Theory. Everything is being pulled away from everything else. Well, that would make us the center of the universe because it's going that way, it's going this way, it's going that way, being pulled away from us. How is that possible? Oh, well, we could be the center of the universe, but I would sort of doubt that. All right, let's see what she has to say for the final nail in her coffin.
Will be the final nail in the coffin. The new data comes from radio telescopes and it measures the motion of Earth through space, kind of. Einstein taught us that speaking of motion in absolute terms is meaningless. We can only speak of motion relative to something else. On Earth, we usually talk about motion relative to the surface of Earth. In space, well, it's not so clear which relative motion is meaningful. One thing you can look at is the cosmic microwave background, the afterglow of the Big Bang that fills the whole sky almost perfectly evenly. It looks a tiny bit hotter.
It's a typo.
In one direction and cooler in the opposite direction. That hot-cold pattern is basically a giant Doppler effect, and from its size we can work out our speed relative to this radiation. From the microwave background we know that the solar system is moving at about 370 kilometers per second relative to this cosmic rest frame in a particular direction on the sky. That's roughly 1,000 times faster than a passenger jet, but still less than 1% of the speed of light. We can also infer our motion from matter instead of radiation. Galaxy colors should be a little slightly shifted to the blue in one direction and a little bit shifted to the red in the opposite direction. If the standard model for the universe, the one with dark matter and dark energy, was right, then these two motions, the one we infer from the cosmic microwave background and the one we infer from the galaxies, should be the same. But
that's a little confusing for the average person. Let me try to break that down. All right, look at this. Cosmic microwave background dipole. That's us. We're a dipole. Cosmic microwave background dipole. That's what they're seeing in our solar system, apparently. That's the way I'm taking this. All right, I'm going to let her continue on, but she's saying that this is the afterglow of the Big Bang, where everything from nothing went to everything. So what they're saying is everything was down here, it all smashed together, one little tiny ball, and all of a sudden it went boing, and then it started pulling the light with it. Well, that's why the light is slowing down. It's shifting. A red shift means that the light coming to us should have been red, but now it's red. I mean, should have been green, but now it's red. And green means this is faster, and I'm going to show this. I can prove this. But now it's shifted down to red. Why would it do that? Well, because it hit a bunch of stuff in front of it, and it slowed it down, down, until it went down to red. I'm going to show you green and red in the same shot. and how much faster the green is than the red. But we know that we can speed up light, and we know that we can slow down light, and we know that if there's anything in between the source of the light and here, or us, it's going to slow it down. It's no question about it. And there's a ton of stuff out there. All right, that's fabulous, because this is brand new to me. I didn't know that the whole, I don't know whether this is the universe or our solar system, is a dipole. They say this is the afterglow of the Big Bang. So, as all matter started being pulled away and light is being pulled away, they say that's why it shifts to the red. No, it's just slowing down. I think I've made that pretty clear. Here we go.
Fills the whole sky almost perfectly evenly. It looks a tiny bit hotter in one direction and cooler in the opposite direction. That hot-cold pattern is basically a giant Doppler effect, and from its size we can work out our speed relative to this radiation. From the microwave background, we know that the solar system is moving at about 370 kilometers per second relative to this cosmic rest frame.
Okay, I hope that made sense to you, that there is light that comes and it travels and slows and slows and slows and slows and slows, and eventually it's just sort of drifting around. And things bang into it and you get this glow, but it's like a, and as a matter of fact, Fermilab said it's like the head of a root beer. It's just all bubbly, and things pop on and off when they get hit by little whatever they get hit by. Electrons or protons or big chunks. And my claim is, and I think everybody knows this by now, that there is nothing but these little tiny particles, and every one of them is a dipole. There's a positive and a negative, just like a bar magnet. And at 1839 or so, right in that area, they become stable. And I can't tell you why. It's just like, for some reason, and somebody might be able to do it with some higher math, figure out why so many exact particles have to surround a black core. And inside there is going to be the dark matter. And the dark matter appears to be the same size as the white matter. Well, the white matter can get big and get small. That's the funny thing about it. But anyway, that's what we've always seen. We've never seen the dark matter because you can't see it. It doesn't radiate, it doesn't absorb, and it doesn't reflect. The only way you can see it is if there's a glowy edge behind it. Precisely what they say at Fermilab. They see the black one with a glowy edge, and then they see the white one get big and get small. I've shown that very clearly. Here's what they're doing at Fermilab and CERN. They're smashing these huge things together, and they're going flying, and bits and pieces are going everywhere. And they will get down into the dark matter. And the dark matter will float around here too, but you just won't see it. It's there. But it's dark. It's dark. It doesn't reflect. It doesn't do anything. But if it gets on top of a white area, which means you have a glow around it, then you can see it. And they have seen that. Exactly that. As we have, because dark matter is part of light. Okay, these are the particles they found at Fermilab, which are the two smallest particles they can find. And there's the black one, which has the glowy edge around it. It's exactly what it says in the article. It says they see them, but they have a glowy edge around them, and that's one size fits all, never changes. You can magnify them, but the one size is it. This one can get huge and get small, and that's what they claim. And they say that one has no mass, but it has a field. This one has all the mass. It's the dark matter. We did this with light. This is with light, and I'm going to show you some better shots in a second. That's what a photon is. Now, this is what I had the arguments with CERN and Fermilab and all of them, virtually all of them, is that they said you can't see that. It's impossible to see photons. I said, no, the way we did it, we can see it. You guys smash big, huge particles, so you can't see anything. You just got a bunch of debris. They want to see this. which is what they did see, the muon, the electron for showers. The muon, which is a black ball, just kept on going. Never changed size. They don't change size. They don't do anything other than push. They used to call them bosons. Now they're gluons, and these two together are gluons. Now you see how that one's big and fluffy and that one's not so big? What'll happen is this one here will get fluffier and fluffier as it pushes through the particles in front of it. It will glow and glow, and then it will flip. And then this one will be in front. So this one's down spin right now. And then when this one flips to the front, that one goes to the back, it'll be up spin. It's, in my opinion, that's what down spin and up spin is. And we can see that we accelerated the light. We can see that we separated the white from the black. And here it is right there. The black is completely separated from the white. Totally white only in the shower. And that, my friends, is raw electricity. That's really what you want to power things. I think there might be some potential here, but I can't seem to get through to anybody to really look at this. And again, I'm showing you evidence here. And if you look this up, dipole electron flood theory, oh, there's no evidence, there's no support, there's a standard model has no evidence whatsoever, but it's got a lot of support. This has all the evidence and no support. Okay, you saw the blue coming in and slowing down very quickly. You can see it's really packed here. So it's really fast going here. And it's just going to get slower and slower as it goes down. Now, it's still a very powerful particle. You can hardly see that there's two of them here. You can't see that at all until you can see here. You can see they're back-to-back dipoles. Very, very hard to work with the blue. Now, the red's a whole different story. It's much slower than the blue. It's the slowest. All right, up here is the blue, and in the middle is the green, which I'll show you in a moment. But again, these are photons. And you see them here because they're being pushed back at. Otherwise, you wouldn't see them until they actually concussed with the thing that they were going to bang into. We're seeing them back here because the thing is sending out a reverse concussive wave that makes it feel like these just hit a wall. Otherwise, you wouldn't see them. All right, now here's the green. Here it comes, zip, and this shows you up and down spin. They don't go sideways, they don't go this way. These are not quite into the photon range yet. Like I said, you would not see them as photons unless they smack into a wall. These things, they just think they're smacking into a wall. And before they do that, they do, there's a the particles aren't quite photons yet. They're still bundles of energy, you see them? It's coming through, and it's sideways this way, and then it's this way. As it gets closer and closer to smashing into this huge reverse wave. You want to see it? Yes, you do. Obviously you do. All right, take your time and think about what you are seeing. This is the laser. Boop, 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 pulsed red laser. Now, as it comes down this way, it starts to literally accelerate. And you say, well, why would it accelerate? Well, of course it accelerate. This did. It's a Venturi. A Venturi causes big things to turn into small things, just like squirting out of a hose. And it comes out of there like a hose. But it starts to pull the particle right out of its own wave. This is the magnetic signature right here. And there's a particle right in the middle of this, and it's a wave-particle duality. Yes, obviously. It's got a field surrounding it. It says, everybody get out of the way, get out of the way, get out of the way. So their fields push back against its field. So there's your wave, and the particle is the thing that creates the magnetic field. So you got the magnetic field inside here being created by the particle. It's coming down, and now the particle is actually ripping itself out from the wave. And at this point, we see the photons. When we were looking, we're seeing the photons right about in here. And the reason we can see them here is because they think they hit a wall. They think this is a wall. Bam! And that's when your photons bounce. And you see the photons. Otherwise, you don't see them until they bounce. And all of these are bouncing now. And you say, well, what are these? Where did this come from? Where did that come from? Why are those things there? It's because this literally is a subatomic, smaller than atoms, nuclear, because it's a nucleus, atomic, explosion. And the particles are separating here, which is fission. And over here, at a certain point, they start to reconnect, which is fusion, fission, fusion, subatomic nuclear explosion. This reverse concussive wave back here is just staggeringly enormous and strong. And up here, it's just like a wall. Up here, you can't even see a wave. You don't see a wave. You see the wave back here? I hope you can see that. You see how strong that wave is? Back here is just a wall. It's literally like a wall coming back. You see, there's no lines there at all. There's no field there whatsoever. It's just a wall. And that's why these lit up like a Christmas tree. They're coming. You just can't see them. You wouldn't know they're there until they concuss with something. And now they are concussing with that reverse field. Now, I know that's dragged it out a little bit, but if you don't understand this, you're never going to understand it. You can see all of these little reverse lines are starting to show up now because that field is just like, think of an atomic bomb, how it spreads out, like same thing, exact same thing. All right, here's what I'm saying is happening. The particles right here, this is the beginning of the wave of shooting the laser. So up to here, it hasn't hit there yet. So the particle is right here. But it's got a wave surrounding it because it's got a magnetic field. And it's pushing that magnetic field forward, pushing it to everybody else's magnetic field. These little dots aren't glowing for nothing. They're glowing because they're being pushed out of the way as the light goes through the air. All right, it's got to push it. The air is full of all kinds of different, gases. And every one of those has a field surrounding them because they got particles surrounding all of the atoms to create the gases. This is get out of the way, it glows, they glow a little bit, it glows a lot. These coming behind it, these are more pulses. They've already cleared the way out, so they don't have to impact so much. So that's why they're not as impact glowy as this one, because this one says get out of the way, and they say, oh no, you get out of the way. And it's a fight. Push to shove always creates the most glow. The most impact, the most glow. All right, so you've seen how the particles somehow, I don't know what's going on between here and here, why they look like they look, but they're starting to get energy. And this one is right dead center heading there, so it shows up as a photon. And that one gets a more intense photon, and then they explode in this area. But they are this is the construction of a photon. Now, this is a red photon. If it was green, it would be like this, but it could be identical to that, and which I'm going to show you. And if it was blue, it would be down here, and it'd be so fast you wouldn't be able to see the particles. And that's exactly what we have found, as I will show you. Now that's a green photon. It's identical. There is no difference whatsoever to the actual particle. The particle itself is identical. There's no difference. The difference is the spin and the speed, and that I can show you here too. This is the red, and it's much slower and much less powerful than the green, which is right above it. And it actually causes them to barrel roll. That's not standard. They're always up and down spin. These are spinners in a circle. They're coming like this, you see? That's because this one's pushing them out of the way and making them barrel roll. But it's the same particle, the same particles. Just one's not going as fast as the other one. All right, here's the problem. Is they're working just splashing things everywhere. And they see the little bitty ones. These are the little bittiest ones they see. But then they see X particles. Could be this big, could be that big, could be anything you want. Because they're starting with gigantic particles like this. We're starting with the tiniest particles. We don't have to dig through all this stuff. We're way ahead on that. And again, these are the particles from Fermilab. That's their article. This one has the mass and a glowy edge. This one has all the energy, but it doesn't have any mass that they can determine. I agree with those statements, 100%. That's what we found. And that's these from Rod and I, what we did here. And these are the particles. I showed you the different particles, the same particle. Just the speed is faster, that's all. And it's exactly what they're saying. Only they think it flaps like a wave, but it doesn't. It spins like a circle. Let me show you how light spins. This is how light spins, just like a drill. And the red is slow enough so that we can actually see the effect of the drill. Now, when it comes out the other side of the Venturi, this is on the wall on the back, the light. Most of it comes through, you can see it's going to catch you here and catch you here. Most of it's going to be glowing in the center. Then you get less glow, and then you get into the red spectrum. So it's not at all accelerated out in this area. But it does have the propensity to keep each other away from. So it comes down and says, you stay away, you stay away, you stay away, you stay. And it sets up these patterns. That's from a circular. That's light in a circle. It spins in a circle. It doesn't flap in a wave. They say it flaps this way and this and it does and this and makes these patterns like that. No. These are, some go this way, some go that way, some go each way, but it doesn't matter. When they get on the other side of here, they don't want other ones next to them. They want them pushed away. That's the whole idea of light. It says, you stay away from me, and I'll stay away from you. And that's why they set up these lines. They call them interference patterns, but they're repulsion patterns. You want to see something cool? Look at this now. You've seen this. We accelerated the light, exploded it here, and only the white came through. Well, what do you think happens right over in this area? It's coming back to the black. There's no question it's coming back to the black. And I can show you that in extreme detail, but what I'm going to show you now is looking into that. And where the biggest, brightest smash is right in the center here, sending off all of these particles, turning back into normal particles. You see this? This is like a dish of dark matter. It must be. It's like a dish. You see how these are big fields like this here? And then the white coming through here is smashing into almost like a skin of water. And they all turn into these particles, which are light particles. Back from what they were before, they split, and now they came back to what they are supposed to be. They would call these Higgs fields. Now, the only one that can make a lot of sense to me, the one that does make a lot of sense, is this one here. It comes up here. Now, what is supposed to happen when that white comes here? It's going to reattach to a black. As far as I'm concerned, this this, if you followed this around, that would be a huge dish. And that's splashing right into the middle of the water of that dish, of the blackness of that water. And this one here is catching up. You see the black, the white, black, white, black, white, and then all of a sudden it starts to spin. And that's the spin. I can't tell you why it does that. But you know, the crazy thing is, on the other side, before it hits the Venturi, it spins too. I showed you how light spins. So light is a spinning particle. In my opinion, there's no point that light doesn't spin. Light could sit around as a particle that had no energy, yes, as the cosmic microwave background, where it's a particle, it's got a magnetic field, but if it doesn't hit anything, it just doesn't do anything. I don't know what it would look like. It wouldn't have that glow around it. I think this is a reattachment spin. And they're all spinning because they're getting reattached. And they all have dots in them. You really can't see this one all that well, but they have a lot of dots on this side. On the other side, not so many dots. But this is an extreme, and you know, you can see them down here. Let me get a better shot of that. All right, this shows a better shot of all the dots. You see all the dots in there? I'm not sure if there was a different setting on the phone, because all I used was a smartphone. That's what I used too, a Galaxy S3 and a Bosch laser. I have them right here, and they work very well. This is looking into the Venturi. So it didn't damage the phone to use it. He used this for years. I used mine, not as much as he does his, but you see here's another one shooting straight up here, banging right into that spot. And then it starts to try to pull itself into itself or something, I don't know. The reason I had this shot was because of this color. And that's squirting itself out like a little tube of toothpaste. Anyway, these are the dots. They should be all red, but when they jam into each other for an instant, they can become different colors. And this spot here was the one that really intrigued me. That's right, now I remember. Now it's all coming back to me. Here it is. That one right there. Let me bring you up close. You see that one hooking to the left? Bright spot. What's that doing there? What is that doing there? Explain it to me, please. That took me a long time to figure out, and I think I got it figured out, but maybe, maybe not. All right, this should be fun. All right, remember I told you explain something to me. Well, this might have something to do with it. See if you can figure it out on your own. I'm going to just leave it at that. But this was something, this is a one-of-a-kind thing, that as far as I know. You see, this is the beauty of seam wash. You see a ton of things at one time. This is the particles that are being more pushed and shoved. And that's why they're glowing more. When they're out in a space where they're not being really impinging, or somebody's impinging on their magnetic region, they just basically go dark. All right, here's another shot from Rod Warren. Coming through the Venturi, you can see how jammed up the waves are. And the black has squished through here some. The other one, there was no black at all. It was just nothing but white. So you can do some things here, and it's pushing this ahead. In a nuclear explosion, they would call these Whistler waves, and these are the pushing the black particles. And I've shown this with atomic bomb blasts, and there's a house, and when the white hits it, it just burns. It doesn't even move. Not a single thing moves. Just smoke comes off it, and until all the combustion's gone, and then the black hits it, and the house goes. But in a nuclear explosion, it goes so fast you don't see that. In these tests they did, they made it so slow that you could see the house just vaporize. It's atomcentral.com. You can go look them up on YouTube, and that's what it is. The black has all the mass. This has no mass whatsoever and all the energy. Two completely separate components. Now look at this. This is from Rod's nephew, Dylan and Dylan Carpenter. And he sent this to me, I don't know, gotta be 5 years ago. I don't know how to explain it. But anytime there's energy, there's white. What the heck that is, I don't know. What this little pyramid is, I don't know. What any of this stuff is, I do not know. That's the moon. So anyway, that started it. And then Mason jumped in and started showing all kinds of crazy things. I mean, the stuff he's showing, yikes. You saw that. That's only the start of it. But I'm telling you, it's everything is a dipole. But these little dots, some of them, I don't know, I can't really see them all that well. He's got some serious stuff. Let me just put it that way. All right, let's go back to Sabine. Here we go.
Can work out our speed relative to this radiation. From the microwave background, we know that the solar system is moving at about 370 kilometers per second.
All right, so they're basing everything on the cosmic microwave background. Now, I'm not sure how they would base that, because, I mean, how do you read that? The cosmic. Let's just say she's right. Let's just assume that they're right, and there's somehow they are figuring out how fast we're moving relative to the cosmic microwave background. So we'll accept that for now.
Relative to this cosmic rest frame in a particular direction on the sky. That's roughly 1,000 times faster than a passenger jet, but still less than 1% of the speed of light. We cannot.
Is she basing this on the speed of light? If she is, that's just totally wrong, because light does not maintain the same speed. Now, if she is basing it on that, and saying that's why we're moving in this direction, the light is slowing down only so much. So let's see what she says.
Also infer our motion from matter instead of radiation. Galaxy color should be a little slightly shifted to the blue in one direction and a little bit shifted to the red in the opposite direction.
That's because she's saying that light is being pulled and pushed. That's not right.
Standard model for the universe, the one with dark matter and dark energy, was right, then these two motions, the one we infer from the cosmic microwave background and the one we infer from the galaxies, should be the same. But the new study found they just aren't the same. The authors calculated our motion from what's called radio galaxies. These are galaxies with emissions in the long wavelength radio part of the electromagnetic spectrum, most of them billions of light years away. Now, for these
light years, there is no light years. There's no such thing as light in a year. Light just travels at the speed it travels. When it hits things, it slows down. If she's basing this on the speed of light, she's got a serious problem.
These radio sources, one can't measure the redshift, so instead they use a related effect that's called Doppler boosting. This effect makes radio galaxies that we move towards appear brighter, and brighter galaxies are easier to see. So the authors take 3 large data sets for radio emissions and count how many sources they see in different directions on the sky. From this they calculate our relative motion, and what they find is that our motion relative to these galaxies is 3.7 times faster than it should be. The direction is roughly compatible with that inferred from the microwave background. Still, that's a discrepancy with the standard cosmological model of 5.4 sigma. That's a very high statistical significance. So where are we going that quickly? The answer is, well, nowhere in particular. If we extrapolate this motion, it isn't going towards any known structure. It's not the great attractor, it's no known supercluster, it isn't even a void. The only thing I can reliably tell you is that we're going somewhere fast. If you still believe in the standard model of cosmology, then maybe this tells you that there is some dark stuff sitting around us that we haven't properly accounted for, or maybe this model is entirely wrong. If the standard cosmological model is wrong, this could resolve the discrepancy simply because the motion of the radio galaxies doesn't have to agree with that of the cosmic microwave background.
What if the whole idea of light and particles and mass and all that stuff is wrong? And it is. And the theory of Dipole Electron Flood Theory is correct. That changes everything, Sabine. I think we should start by looking at that. You know, you're looking at all these other things and making all these assumptions and, you know, well, what about this, what about that? Well, how about my stuff?